He looked up at the night sky once, really looked. Not the casual glance you give before checking your phone, but the kind of looking that costs you something, and what he felt was not wonder. What he felt was the specific cold terror of realizing that everything he had ever loved, every argument he had ever won, every meal he had ever tasted, every laugh he had ever pulled from a room full of people, all of it, every single atom of it was sitting on a speck of rock, so absurdly small that the nearest star would not even notice if it vanished. And here is the question that never left him after that night, the question that will follow you too, once it takes root. Why do those who try hardest to understand the cosmos end up feeling more lost inside it? Aver, stay with that, because the answer is not what you think it is. There's something Feynman understood that most people who call themselves curious never quite reach, and it is this: the universe does not owe you comfort. It does not organize itself around your need to feel significant. It does not slow down so you can catch up. And the most brutal thing of all, the thing that kept him awake, that kept him scribbling on napkins in the middle of the night, is that what we call space, what we point at when we look up, what we draw in diagrams with neat little arrows and label with confident Latin words, may not be a thing at all in the way we imagine it, not a container, not a backdrop, not a stage on which the universe performs. The word space, spoken with such casual authority in every classroom on this planet, might be the single most confidently mispronounced word in the history of human thought. And that is where this begins. Pues think about a Tuesday evening in late October, the kind of evening where the air has just turned cold enough to remind you that summer was never going to stay. You step outside after dinner, maybe to take out the trash, maybe just to breathe, and you look up, really up. The sky is clear and the stars are doing what they always do, which is absolutely nothing. From your perspective, just hanging there, scattered and silent and impossibly far. And for a moment, maybe 3 seconds, maybe 5, you feel it? That thing, that vertigo that is not quite fear and not quite awe, but lies somewhere between the two, like standing at the edge of something with no railing. Most people blink, go back inside, and never think about it again. Most people let the TV fill back up the space that the cosmos just cracked open in their chest. Bueno, Feynman never went back inside. Not really. He stood in that crack and decided to live there. He would have looked at that same sky and asked a question so simple it sounds almost childish. What is the stuff between the stars? Not the stars themselves, not the planets, not the gas clouds that glow like bruises in infrared photographs, but the in-between, the gap, the silence. What is that made of? And then, because Feynman was constitutionally incapable of accepting a lazy answer, he would have followed that question all the way down into the foundations of physics, past the comfortable explanations, past the textbook definitions, past the point where most people get nervous and change the subject, until he arrives somewhere genuinely strange. If you have spent any part of your life looking at the night sky and feeling something you could not name, then you're already part of this. You're already in the conversation. Hit that subscribe button and come with us, because what you are about to understand will not let you look at the sky the same way again.
This is not a metaphor. This is not poetry.
This is the actual science. The kind that makes physicists go quiet at conferences. The kind that Feynman himself wrestled with and never fully let go. Join this crew of cosmic explorers. Drop a comment below telling us what you felt the last time you really looked at the night sky. Because what you describe, that specific feeling, has a scientific name, and we are going to reach it together before this is over. Now let us talk about what you are actually risking by not understanding this. Déjame pensar un momento, because this is the part where people usually get polite and reassuring, where they say something like, well, it is all very interesting, but it does not really affect your daily life. And that is exactly the kind of comfortable lie that Feynman had zero patience for. Here's the truth, and it is not a comfortable one. If you do not understand the nature of the space between things, if you do not grasp what physics actually says about the fabric of reality at its most fundamental, you are walking through the most important era in human history wearing a blindfold. You are making decisions collectively as a civilization about science funding, about space exploration, about the search for other intelligent life, about the technologies that will either save this species or fail. And you are making those decisions with a model of reality that is centuries out of date. Why do those who try hardest to understand the cosmos end up feeling more lost inside it? Because most of what we teach people about space is a beautiful, functional, but ultimately incomplete story. And incomplete stories are not neutral. They have consequences. Here is one consequence that should make your stomach do something uncomfortable. Right now, at this moment, there are approximately 250 billion galaxies in the observable universe. That is the observable universe, the bubble of space from which light has had time to reach us since the Big Bang. Beyond that bubble, we have no idea. The universe may be infinite, it may be finite, but unbounded. It may be one of an uncountable number of universes that never interact with ours. And in all of that, in all of those 250 billion galaxies, each containing hundreds of billions of stars, each star potentially surrounded by worlds, we have found exactly one place with confirmed, intelligent life. One. This rock, this Tuesday evening trash-taking out rock. Aver, Feynman would ask, does that strike you as strange? Because it should. It should strike you as one of the strangest facts in the history of thought. And the name for this strangeness, the formal scientific label for this cosmic silence that roars at us from every direction, is the Fermi paradox. Named for Enrico Fermi, who once sat down at lunch with a group of physicists and asked with the casual brilliance of someone who does math the way other people breathe, where is everybody? That is the whole paradox in 3 words. The universe is so vast, so old, so full of the raw materials for life that statistically the silence makes no sense. And yet, silence. But here's where Feynman's thinking cuts deeper than the standard telling of the Fermi paradox, deeper than the usual list of possible explanations, deeper than the optimistic shrug that says, well, maybe they are just too far away to communicate, because Feynman was not just asking where the aliens are. He was asking something more fundamental. He was asking what kind of universe would produce this silence. What are the rules of this place, really? What is the actual structure of the space that separates us from whatever else might be out there? And when you follow that question honestly, when you refuse to stop at the comfortable answer, you arrive at something that sounds like a provocation, but is in fact one of the deepest results of 20th century. Physics, space, in any simple, intuitive sense, does not exist. Pues, hold on. Let us be precise, because Feynman would insist on precision. He would say, look, I'm not telling you that there's nothing out there between the Earth and the Moon. Obviously, if you throw a baseball hard enough, it travels from here to there through something. What I'm telling you is that your intuitive picture of what that something is, the idea of space as a kind of giant empty container, a cosmic box inside which things happen, is not what physics actually describes. And the difference between your intuitive picture and what physics actually describes is not a small technical footnote. It is the whole story. Think about it this way. Imagine you have a glass of water. You drink all the water. Now you have a glass of nothing, right? Empty space inside the glass. Simple. That is the intuition. But quantum mechanics, the theory that Feynman helped build into its modern form, the theory that has been tested to a precision that makes every other scientific theory look like a rough sketch. That theory says, no, there is no such thing as a glass of nothing. The moment you remove the water, the space inside the glass is not empty. It is seething. It is alive with something that physicists call quantum fields, and those fields are never under any circumstances at zero. They fluctuate, they hum, they pop virtual particles in and out of existence so fast that you cannot catch them individually. But their collective effect is measurable, real, and has been confirmed in laboratory experiments to extraordinary precision. This is not a metaphor. Espera, this is the actual physics. The Casimir effect, demonstrated first in 1948 and confirmed experimentally with stunning precision in the decades since, is direct evidence that the vacuum, what we casually call empty space, exerts a measurable physical force. Two metal plates placed extraordinarily close together in a vacuum are pushed toward each other by the pressure of the quantum fluctuations in the space between them, because the space outside has more room for fluctuations than the space inside. Empty space pushes things. Empty space has energy. Empty space is not empty. And Feynman, who helped develop quantum electrodynamics, who built the mathematical machinery that describes how light and matter interact through these fields, he understood this better than almost anyone alive. He would sit down and he would say, you want to know what space is? Space is the quantum vacuum, and the quantum vacuum is one of the most violent, energetic, structure-rich environments in the known universe. It just operates on a scale so small, so far below anything your senses can register, that from where you stand, it looks like nothing. It is the most perfectly disguised something in existence. Now, why does this matter? Why should you care on a practical human level whether the vacuum is truly empty or secretly full? Because of what it means for everything we have been asking about the cosmos, because of what it means for the Fermi paradox, because of what it means for the Great Filter. Déjame pensar un momento about the Great Filter. It is a concept introduced by economist Robin Hanson in 1998, and it is one of the most quietly terrifying ideas in all of intellectual history. The argument goes like this: if intelligent life should be common in the universe, given the enormous number of stars and planets and the billions of years available for evolution, then where is it? The silence suggests that somewhere between the formation of a rocky planet and the kind of civilization that can communicate across interstellar distances, there is a filter, a barrier, something that almost nothing gets through. And the terrifying question, the one that should genuinely disturb your sleep, is whether that filter is behind us or ahead of us. If the filter is behind us, if the hard part was, say, the emergence of complex multicellular life, or the evolution of the eukaryotic cell, or the specific improbable sequence of events that produced a brain capable of doing physics, then we might be genuinely rara, genuinely lucky, and the future, while never easy, is at least open. But if the filter is ahead of us, if what awaits every technological civilization is some catastrophic wall that none of them have ever cleared, then the silence of the universe is not the silence of an empty house. It is the silence of a cemetery, and we are the newest headstone being carved. Feynman would not let you sit with that fear without also handing you a tool. That was his genius. He never weaponized complexity to make you feel small. He used it to make you feel capable. And the tool he would hand you here is this: the nature of the quantum vacuum, the fact that space is not empty, but is instead a structured, energetic field-theoretic reality, changes the terms of the Great Filter. Conversation in ways that most people have not yet absorbed. Because if the vacuum is full of energy, if what we call empty space is actually a ground state of something, then the question of what civilizations can do with the physics of space itself becomes radically different from what our intuitive picture would suggest. The energy density of the quantum vacuum, what physicists call the zero-point energy, is, depending on how you calculate it, somewhere between enormous and incomprehensibly enormous. There is a famous discrepancy in physics, sometimes called the worst prediction in the history of science, where naive calculations of the vacuum energy density differ from what we observe by a factor of 10 to the power of 120. That is a 1 followed by 120 zeros. The discrepancy is so large that it is itself a clue, a signpost pointing towards something in our understanding of space that is deeply, profoundly incomplete. Why do those who try hardest to understand the cosmos end up feeling more lost inside it? Because every time physics hands you a firm answer, it comes packaged with a deeper question. And the deepest question sitting at the heart of all of this is, if space is not a container but a participant, if the vacuum is not nothing but something, then what is the geometry of this thing? What is the actual shape, the actual structure, the actual nature of the arena in which everything happens? Bueno, this is where Einstein enters the conversation, and where Feynman's thinking gets genuinely wild. Einstein's general relativity, the theory that replaced Newton's picture of gravity as a force acting across empty space, describes gravity not as a force at all, but as the curvature of space-time. Not space, space-time, the fabric that is woven from both the 3 dimensions of space and the 1 dimension of time, and which bends, curves, stretches, and compresses in response to the presence of mass and energy. The Earth does not fall around the sun because some invisible rope pulls it. The Earth follows the curved geometry of the space-time that the sun's mass has warped, like a marble rolling around the inside of a bowl. Except the bowl is 4-dimensional and it is made of the structure of reality itself. Now, Feynman had a complicated relationship with this picture. He respected general relativity enormously. He also spent his career working in quantum mechanics, and he knew better than most that these two theories, general relativity and quantum mechanics, the two greatest triumphs of 20th century physics, are fundamentally incompatible with each other. They cannot both be right in their current forms at the deepest level of reality. They give contradictory answers about what happens inside a black hole, about what happened at the moment of the Big Bang, about what space itself is made of at the Planck scale, the smallest possible length, which is approximately 1.6 times 10 to the negative 35 meters, a distance so small that writing it out feels almost like a joke. Whereas at the Planck scale, the smooth, curved geometry of general relativity breaks down completely. Space, at that scale, is not smooth. It is not a fabric. It is, according to most approaches to quantum gravity, something more like a foam. A quantum foam where the geometry of space-time itself fluctuates wildly, where the topology of space can change, where what we mean by distance and direction and the structure of before and after becomes something almost unrecognizable. John Wheeler, one of the great physicists of the 20th century and a man who influenced Feynman directly, coined the term quantum foam for this picture, and it is one of those ideas that is simultaneously beautiful and deeply unsettling. Think of it this way. When you look at the ocean from an airplane, it looks smooth, a flat, glittering plane. But if you descend, if you get close, you see waves. Get closer and you see ripples. Get close enough and you are inside a chaos of spray and turbulence where the concept of a smooth surface has lost all meaning. Space is like that. From the scale of galaxies, it looks smooth, obedient to Einstein's equations. But descend to the Planck scale, and the very concept of a smooth, continuous, empty space dissolves into something else entirely. And here's what this means for the Fermi paradox, for the great filter, for the terrifying silence of the universe. If space is not a passive, empty container, but is instead a dynamic, energetic, structure-rich entity in its own right, then any sufficiently advanced civilization would not simply be traveling through space. It would be interacting with it, manipulating it, reading it. And the question of whether such interactions are possible, whether they are the key to crossing the unimaginable distances between stars, whether they are precisely what the great filter is separating those who discover them from those who do not, that question is not science fiction. It is the current frontier of theoretical physics, the distance between our solar system and the nearest star, Proxima Centauri, is approximately 4 light years. That means light, the fastest thing in the universe, traveling at approximately 300,000 kilometers per second, takes 4 years to make that journey. Our fastest spacecraft, the Voyager probes, launched in 1977, are currently in the outer reaches of our solar system, and they will not reach even that nearest star for tens of thousands of years. Not centuries, tens of thousands of years. And Proxima Centauri is our nearest neighbor. The Milky Way is 100,000 light years across. The nearest large galaxy, Andromeda, is 2.5 million light years away. The observable universe is 93 billion light years in diameter. Aver, let those numbers sit in your body for a moment, not just in your head, in your body. Feel what they do to your posture. Notice where your breath goes, that tightness across the chest, that slight heaviness in the gut. That is not anxiety, that is your nervous system accurately processing the scale of the problem. That is your body responding to a true thing. Feynman would say, good, stay there, because the people who flinch away from that feeling, who reach immediately for the comfortable reassurance, those people never ask the right questions. The right question, the one that Feynman's thinking demands, is not, how do we build a faster rocket? The right question is, are we sure we understand the nature of the space we are trying to cross? And the answer, as we have been building toward, is no, we are not sure. We are not even close to sure. We have two magnificent theories, general relativity and quantum mechanics, that describe the universe with extraordinary precision at the scales they are designed for, and they fundamentally disagree about the nature of space at its most basic level. And in that disagreement lives the possibility, not the guarantee, but the genuine scientific possibility. That space is not what we think it is, and that what we think of as an impassable distance might, under a physics we do not yet fully have, be something very different. Why do those who try hardest to understand the cosmos end up feeling more lost inside it? Because they are honest enough to sit with the incompleteness. because they do not paper over the cracks, and the cracks in our understanding of space are not cosmetic. They go all the way down. Espera, let me tell you about a third week in November in a physics department in California in the early 1960s. Feynman is teaching, as he always was, not lecturing in the formal sense, but thinking out loud in front of people, which is something different, something rarer, something that requires a kind of intellectual courage that most academics cannot sustain. A student, young, clearly brilliant, clearly nervous, puts up her hand and asks him, "What is a photon, really? Not the equation, not the probability amplitude. What is it really in the world?" And Feynman pauses, not for effect. He actually pauses because the question is genuinely hard, and he is not the kind of man who pretends otherwise. And then he says, "That is the question, isn't it? That is the one we keep circling." And he goes to the board and he starts drawing, not equations first, pictures first, the way he always did, because he understood that your intuition has to be rebuilt before your mathematics can mean anything. What he was drawing was a picture of how a photon, a particle of light, travels through space. And what that picture shows, what quantum electrodynamics actually tells us, is something that should permanently alter how you think about the word space. A photon does not travel from point A to point B through the shortest path, the way you would drive from your house to the grocery store. It travels, in a precise and mathematical sense, through all paths simultaneously, every possible route. The straight line, the curving path, the path that goes via Mars, the path that goes via the Andromeda galaxy, all of them with different probability amplitudes that mostly cancel out, leaving the straight line as the dominant result. But the key word is mostly. The other paths are not zero. They contribute. They are part of the physical reality of what a photon is and how it moves. And what does this say about the space those paths move through? It says that the space is not a fixed, static geometry through which things move. The space is part of the quantum mechanical description of the thing moving through it. The particle and the space it moves through are not two separate things. They are aspects of a single quantum reality. The separation between the traveler and the road is not as clean as it looks. Bueno, now we are getting somewhere that matters. Because if the traveler and the road are not cleanly separable, if the quantum description of a particle is inseparable from the quantum description of the space it inhabits, then the idea of space as a pre-existing container, empty and waiting, is not just incomplete. It is the wrong picture at the foundational level. Space is not the stage. Space is part of the performance, and this is where the holographic principle enters and where things get genuinely, bracingly strange. The holographic principle developed in the 1990s largely through the work of Gerard 't Hooft and Leonard Susskind, and given its most precise and mathematical form in the work of Juan Maldacena, proposes something that sounds like science fiction but is, as of right now, one of the most actively researched ideas in theoretical physics, that the three-dimensional reality we experience, including the space we move through, may be entirely encoded in information that lives on a two-dimensional surface surrounding it. Think about a hologram. A hologram is a two-dimensional object, a flat piece of photographic film, that encodes a three-dimensional image. When you illuminate it correctly, the three-dimensional picture emerges. The depth, the volume, the apparent space inside the image, all of it is encoded in the flat surface. The holographic principle suggests that the universe may work the same way, that the three dimensions of space we experience, with all their depth and volume and the vast distances between stars, may be a kind of projection, encoded in a lower dimensional structure at the boundary of the universes. Pues this is not a poetic metaphor. The mathematics of this, specifically the anti-de Sitter space and conformal field theory correspondence, known as ADS or CFT, is one of the most precisely tested correspondences in theoretical physics. It has been used to calculate properties of real physical systems, including the behavior of certain materials in condensed matter physics, with remarkable accuracy. It is not proven as a description of our actual universe, but it is not speculation either. It is a working research program with real results. And what it implies for the nature of space is, to use Feynman's own standard of strangeness, appropriately strange. It implies that space might not be fundamental. It might be immersion. The way that temperature is not a fundamental property of nature, but emerges from the collective behavior of enormous numbers of atoms, space itself might emerge from something deeper, something that does not look like space at all. If space is emergent rather than fundamental, then the question, what is between the stars, gets a very different answer than the one your intuition provides. The answer is not nothing, and it is not quantum foam, and it is not even a field in the simple sense. The answer might be information, quantum information, the relational structure of entanglement between quantum systems, woven together in a pattern so complex that what we experience as three-dimensional space is the large-scale, coarse-grained shadow of that pattern. This is not a comfortable idea. Déjame pensar un momento about why. Because if space emerges from quantum entanglement, then the structure of space, the distances between things, the very geometry of the cosmos, is not a fixed backdrop against which events occur. It is a dynamic consequence of physical relationships. Change the entanglement structure, and you change the geometry. And this means, in principle, that a sufficiently advanced understanding of quantum information and entanglement might give a civilization the ability to do things with space that look, from the outside, like magic. Compressing distances, threading connections between points that seem far apart, doing things that our current physics would describe as impossible but that a deeper physics might describe as merely very difficult. The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, is a solution to Einstein's field equations that describes a spacecraft traveling faster than light not by moving through space, faster than light, which is forbidden, but by contracting the space in front of it and expanding the space behind it, so that the spacecraft itself is always moving locally at sublight speeds while the space around it does the work. The physics of whether such a thing is practically achievable is still deeply contested. The energy requirements calculated naively are absurdly enormous, and there are serious theoretical objections. But the fact that Einstein's own equations admit such a solution is itself remarkable. Space, in general relativity, is not a rigid thing. It bends, it stretches, it can, in principle, be engineered. And here is the question that should make your spine do something. If such engineering is possible, even in principle, then the great filter might not be a wall at all. It might be a door that requires understanding the true nature of space to open. And the civilizations that went silent in the Fermi paradox might have gone silent not because they were destroyed, but because they learned to move through the cosmos in ways that are simply invisible to a civilization, still pointing radio telescopes at the sky and listening for carrier waves. Or they might have been destroyed. That is the other possibility, and it is the one Feynman would insist on keeping on the table, because he was not a man who preferred the comforting explanation. He was a man who preferred the true one, and he would remind you that the universe does not owe us a survival story. The great filter, if it is ahead of us, could take many forms. A gamma ray burst from a nearby star, which releases more energy in a few seconds than the sun will emit in its entire lifetime, and which would strip away the ozone layer of any planet in its path, sterilizing it from orbit. A runaway artificial intelligence that optimizes for a goal incompatible with the survival of its creators. A nanotechnology catastrophe. Climate destabilization past a tipping point from which no recovery is possible. Or something subtler and perhaps more terrifying. The simple failure to maintain the intellectual culture necessary to keep doing science. The slow, comfortable embrace of certainty over curiosity. The decision made not dramatically but incrementally to stop asking hard questions. Why do those who try hardest to understand the cosmos end up feeling more lost inside it? Because they see this possibility clearly. They see that the most dangerous thing a civilization can do is not build a weapon. It is stop being curious. Because a civilization without curiosity is a civilization that has already accepted its own irrelevance, and the universe, in its vast indifference, is perfectly willing to confirm that acceptance. Feynman had a phrase he used. He said, "The first principle is that you must not fool yourself, and you are the easiest person to fool." He was talking about scientific integrity, about the discipline of testing your own ideas with the same rigor you apply to everyone else's. But in the context of the cosmos, in the context of the Fermi paradox and the great filter and the nature of space, this principle has an existential weight that goes far beyond laboratory methodology. Because the story we tell ourselves about our place in the universe, the story that says we are at the center, we are the point, we are the inevitable outcome toward which all of cosmic history was building, that story, is the oldest, most persistent, most dangerous self-deception in human history. And the universe has already shown us, repeatedly and without apology, exactly how it feels about that story. It feels nothing. It does not feel, that is the point. But here's where the light comes in, and I mean that almost literally, because all of this, the quantum vacuum, the holographic principle, the emergent nature of space, the possibility of a physics we do not yet have, all of it points not toward despair, but towards something that Feynman would call the correct emotional response to the universe. Passionate, relentless, almost unreasonable curiosity. The fact that space is not what we think it is not a reason for existential paralysis. It is the most exciting scientific frontier in human history. It is the place where the next revolution in physics will happen. The revolution that reconciles general relativity and quantum mechanics, that explains the vacuum energy discrepancy, that tells us what space actually is at the Planck scale, that might, in doing so, open doors to the cosmos that are currently invisible to us. And the people who will walk through those doors, who will do that physics, who will write those equations and test them and build on them, those people are alive right now. Some of them are watching this. Some of them are young enough that the revolution will happen within their working lifetimes. Bueno, let us talk about what you can actually do with this. Not theoretically, practically, how does understanding the non-emptiness of space, the quantum nature of the vacuum, the emergent nature of space-time, change the way you actually think and act and engage with reality? The first thing it does is correct your sense of scale. Not just the numerical scale, the incomprehensible distances and timescales, but the conceptual scale, the scale of how big the questions are and how early in the process of answering them we are. Humans have been doing modern physics for roughly 100 years. 100 years in a universe that is 13.8 billion years old. We are, in cosmic terms, infants who just learned to speak. And what we have managed to say in that 100 years, the general theory of relativity, quantum mechanics, quantum electrodynamics, the standard model of particle physics, the discovery of the expanding universe, the detection of gravitational waves, the imaging of a black hole. These are extraordinary achievements, but they are not the end of the story. They are the beginning of the second chapter. The second thing understanding the nature of space does is recalibrate your relationship with uncertainty. Most people experience uncertainty as a problem, as a gap to be filled as quickly as possible with the nearest available explanation, even if that explanation is wrong. Feynman experienced uncertainty as the most interesting place to live. He once said, "I'd rather have questions that can't be answered than answers that can't be questioned." And the questions at the frontier of our understanding of space are the most profound questions that cannot currently be answered. What is space made of at the Planck scale? Why does the observed vacuum energy density differ so dramatically from theoretical predictions? Is space fundamental or emergent? Are there dimensions beyond the three we experience? Is the universe, at the deepest level, made of information? These are not rhetorical questions. They are active research programs. They are the questions that physicists at every major institution on this planet are working on right now, with mathematics, with experiments, with the kind of relentless intellectual effort that Feynman modeled throughout his life. And the correct response to these questions, the response that keeps you engaged with reality rather than retreating from it, is not to reach for a premature answer. It is to stay in the question, to let it open you rather than close you. The third thing, and perhaps the most practically important, is this: understanding that space is not a passive empty container, but a dynamic, energetic, structure-rich reality changes your sense of what is possible. Not in a vague, motivational poster sense. In a specific, physics-grounded sense. The history of technology is in large part the history of discovering that things we thought were empty were full, and then learning to use what was in them. The air was empty until we discovered it was full of molecules and learned to build engines that used their pressure. The space between atoms was empty until we discovered it was full of electromagnetic fields and learned to build radio transmitters. The vacuum was empty until we discovered it was full of quantum fluctuations and learned to measure the Casimir effect. Each of these discoveries opened technologies that the previous generation would have called magic. Feynman would ask, what will we find in the next layer? What is in the space that current physics describes as a quantum vacuum? What is in the structure of space-time at the Planck scale? What is in the informational fabric that the holographic principle suggests underlies the geometry we experience? We do not know, and that not knowing is not a failure. It is an invitation. It is the universe, in its vast, indifferent, impersonal way, leaving the next door unlocked for whoever has the patience and the courage to keep knocking. Espera, let us return to the question one more time, because it has earned its answer now. Why do those who try hardest to understand the cosmos end up feeling more lost inside it? Here is the answer that Feynman's whole life and work points toward, because understanding the cosmos is not a process that ends in certainty. It is a process that ends in better questions. And the feeling of being lost, that specific intellectual vertigo that comes from really confronting the strangeness of the universe, is not a sign that you're failing. It is the sign that you are finally paying attention. It is the sign that you have stopped fooling yourself. It is the sign that your model of reality has become honest enough to reflect some of the actual complexity of what is out there. The person who feels no vertigo looking at the night sky has not achieved calm. They have achieved numbness. And numbness in a universe this strange and this dangerous and this full of unanswered questions is not a virtue. It is the first step toward the great filter. Boys, here is what Feynman would want you to leave with. Not a list of facts, although facts are wonderful and we have had several tonight. Not a set of conclusions, although conclusions are useful when they are honest. What he would want you to leave with is a posture, a way of standing in relation to the universe. The posture of someone who is genuinely, uncomfortably, joyfully aware that they do not know, that the space between the stars is not a simple emptiness, but a seething, structured, energetic, possibly informational reality that current physics cannot fully describe. That the silence of the universe in the face of the Fermi paradox is one of the most important unsolved problems in the history of science. That the great filter might be behind us or ahead of us, and that which it is depends in part on the choices this civilization makes about whether to keep doing science, whether to keep funding curiosity, whether to keep producing people who are willing to live in the hard questions. The posture of someone who looks at the night sky and feels the vertigo and does not look away. Bueno, because out there, in those incomprehensible distances, in that quantum frothing non-emptiness that we casually call space, is either the graveyard of every civilization that tried and failed, or the unexplored territory of everything this species could still become. And the difference between those two outcomes might be nothing more, and nothing less, than whether enough of us decided that the universe is worth understanding. Feynman used to end his talks sometimes with a simple thing. He would look at the audience, really look, the way he looked at problems with that direct, undecorated attention that made people feel both seen and slightly accountable. And he would say something like, "Isn't it remarkable?" Just that. Isn't it remarkable that we can ask these questions at all? That on this small, warm, improbable planet, around this ordinary star, in this unremarkable corner of one galaxy among 250 billion, something happened that allowed atoms to arrange themselves into a configuration that can look up and ask what space is made of. That can feel the vertigo of its own smallness. That can be genuinely troubled by the silence of the universe. Déjame pensar un momento about what it would mean to lose that. What it would mean for a civilization to reach the point where it has access to the most profound questions ever formulated, where the tools to begin answering them exist, where the mathematics is there, and the experiments are possible, and the minds capable of doing the work are being born every day, and then to simply stop, to see that the comfort is more important than truth, that certainty is more important than accuracy, that the feeling of knowing is worth more than the discipline of actually finding out. That would be the real great filter. Not an asteroid, not a gamma ray burst, not a rogue artificial intelligence. The filter that would be hardest to survive and hardest to forgive would be the one we chose. The one built out of incuriosity and comfort and the slow, voluntary surrender of the capacity for wonder. And that, more than any cosmological catastrophe, is what Feynman was afraid of. Not the universe destroying us from outside, but us destroying our relationship with the universe from inside, closing our eyes to the strangeness, mistaking the map for the territory, confusing the word space spoken with such casual authority for the actual, wild, non-empty quantum frothing. possibly holographic, potentially emergent, genuinely extraordinary reality that the word points toward but does not contain. Avera, the next time you step outside on a clear night, the next time the sky is dark enough and your eyes have adjusted and the stars are doing what they always do, which is absolutely nothing from your perspective, just hanging there, scattered and silent and impossibly far, try something. Try not to look away from the vertigo. Try to hold for just a moment the full weight of what is actually out there, a quantum vacuum that is not empty, a space-time that is not a container, a universe that is not silent in the way we thought, a great filter that may be behind us or ahead of us, a cosmos so strange that our best physics cannot yet fully describe its own foundations, and in the middle of all of it, on this small and improbable rock, a temporary arrangement of atoms that somehow learned to ask questions about the space between stars. Isn't that remarkable? Just that? Isn't it remarkable? And the answer, the only honest answer, the one that Feynman spent his whole life demonstrating is yes, yes it is. It is the most remarkable thing any of us will ever be part of. And the only appropriate response to that, the one that honors the strangeness and the scale and the terror and the beauty of it, is to keep looking, to keep asking, to refuse with everything you have, to stop wondering, because the universe is not done being strange, and neither are we.